Hey everyone, welcome to this quick reference explainer. Today we are diving straight into Chapter 19 of your Class 11 economics notes, and we're zeroing in on something absolutely crucial, the coefficients of dispersion. If you've ever stared at a massive data set and wondered, how on earth do I compare its volatility to another totally different set of data, well, you are definitely in the right place. We're going to cover all 6 of these formulas today. Think of them as the secret decoder rings for statisticians and economists. So grab your notebooks, get comfortable, and let's get ready to lock down these coefficients so you can easily copy them into your notes.
Okay, here is our quick roadmap for today's explainer. We'll start with the meaning of dispersion, then move on to range and quartile coefficients, followed by mean deviation coefficients. After that, we'll tackle standard deviation and variance, and finally, we'll wrap it all up with the ultimate formula review.
All right, let's jump right into Section 1, the meaning of dispersion.
Before we actually get into the math, we need to ground ourselves in what we're actually measuring here. According to your notes, dispersion is the extent to which various values of a series tend to disperse from each other, or from an average. Basically, we're looking at how spread out the data is, right? Not just the average itself. Because think about it, you could have 2 completely different sets of data with the exact same average, but one might be tightly clustered together while the other has numbers literally flying all over the place. Dispersion measures that scatter. And when we're talking about coefficients of dispersion, we mean relative measures. These are ratios that let us compare the spread of 2 totally different series, even if one is measured in, say, kilograms and the other is in dollars. Pretty cool, right?
Let's move on to Section 2, range and quartile coefficients.
Okay, grab your pens. Here is our very first formula, the coefficient of range. It's simply h minus L divided by h plus L. In this case, h is the highest value in your series, and L is the lowest value. It really doesn't get more straightforward than this. By taking the difference between the highest and lowest values and dividing it by their sum, you completely strip away the units of measurement. You're just left with a pure ratio. It's a fantastic, super quick way to understand the total span of your data. But keep in mind, it does rely entirely on those 2 absolute extremes. Now, moving on to the coefficient of quartile deviation. What's super interesting here is how this actually mirrors that range formula we just looked at, but it narrows the focus down to the middle 50% of your data. The formula is Q3 minus Q1 divided by Q3 plus Q1. You know how that previous range formula could be easily distorted by some crazy outliers? Well, this formula is your fix for that. It literally ignores the top 25% and the bottom 25% of your data entirely. It's strictly focusing on the spread of those typical middle-of-the-pack numbers. And just a quick reminder to jot this down if you need a little refresher on the terms. Q3 represents your upper quartile, which is the 75th percentile mark of your data. Q1 is your lower quartile, or the 25th percentile mark. Finding these quartiles might mean you need to construct a cumulative frequency table, depending on whether your data is individual, discrete, or continuous. But once you actually have them, plugging them into this coefficient formula is just an absolute breeze.
Doing great so far. Let's switch gears a bit for Section 3, mean deviation coefficients. Here we're looking at the coefficient of mean deviation from the mean. We take the mean deviation from the mean, which is denoted as MD subscript x bar, and we simply divide it by the mean itself, which is x bar. Think of that numerator as the average distance every single individual observation is from the group's overall average. By dividing that distance by the mean itself, boom, you get your coefficient. It basically answers the question, relative to the size of the mean, how far off is our typical data point?
And we do something very similar for the median. We divide the mean deviation from the median, denoted as MD subscript M, by the median itself, which is just M. Now, you might be wondering, why would we even use the median instead of the mean? Well, if your data set happens to be highly skewed by just a few massive numbers, the median is actually a much more accurate representation of a typical value. So calculating your mean deviation relative to the median can sometimes give you a far more reliable coefficient of dispersion for that skewed data.
All right, we are on the final stretch of formulas. Section 4, standard deviation and variance.
This one is incredibly common. The coefficient of standard deviation is simply your standard deviation, which is that little lowercase Greek letter sigma there, divided by the mean, x bar. Standard deviation is mathematically rigorous because it squares all those deviations from the mean, which wipes out the negative signs and gives extra weight to those large outliers, all before taking the square root. But the good news? Once you've actually done the heavy lifting of calculating sigma, finding the coefficient is literally just one simple division step. This brilliantly illustrates what that sigma variable actually represents, specifically if you were using the direct method for continuous data. It's the square root of the sum of f times x squared divided by n. Now, your notes actually detail a few different ways to find sigma, right? Like the direct method, the shortcut method, and the step deviation method. But honestly, it doesn't matter which method you use to find the standard deviation itself, because the final step to find its coefficient is always exactly the same. You take your sigma result and divide it by your mean. Simple as that. And finally, to get the coefficient of variance, you literally just take that previous standard deviation formula we just talked about and multiply the whole thing by 100 to turn it into a percentage. So it's sigma divided by x bar times 100. Honestly, this is arguably the most practical formula in the entire chapter. By expressing the dispersion as a percentage, it makes comparing totally unrelated data sets just incredibly intuitive. For example, a stock portfolio with a 5% coefficient of variance is objectively way less volatile than a portfolio with a 20% coefficient. It just puts everything on a standard, even playing field that anyone can understand.
Okay, let's lock this all in. Section 5, the ultimate formula review. Go ahead and hit pause right here. We've put all 6 formulas cleanly on screen so you can easily copy this complete list directly into your notes for the big exam. Here they are, side by side, exactly as they appear in your Vikram Tutor study material. From range at the top, handling our absolute extremes, all the way down to the coefficient of variance at the bottom, which translates our standard deviation into a clear percentage. Seeing them all together really highlights how similar they are conceptually, doesn't it? You're pretty much always taking a measure of absolute spread and dividing it by a measure of central tendency, or a sum of extremes. That's how you get that pure comparable ratio. Before I let you go, I want you to think about this question. Because remember, these coefficients don't just solve math problems on a test, they reveal the real story hiding behind the numbers. If dataset A and dataset B both have an exact average of 50, but dataset A has a coefficient of variance of 2% and dataset B has a coefficient of variance of 45%, well, what does that actually tell you? It tells you that dataset A is highly consistent and reliable, while dataset B is chaotic and completely unpredictable. The average alone lied to you, but the coefficient of dispersion revealed the absolute truth. Keep that in mind as you review your notes. Thanks for joining this explainer, and best of luck on your economics exams.